Chapter number 8, we were talking about ionic bonds, and when we talked about ionic bonds, we said that it was going to be formed from the transfer of electrons. In chapter number 9, we're going to put that with chapter 8 when we go ahead and study electrons, and we're going to be talking about covalent bonding and a little bit about acids in chapter number 9. Again, when we talked about an ionic bond, we said that that was any compound that was formed from the transferring of electrons. Basically, what we're saying is one atom is going to gain electrons while another atom is going to lose electrons, typically between a metal and a non-metal. Some of the properties that we said for ionic compounds included crystalline structures, high melting points, high boiling points, electrical conduction when the particles are free moving or when they were melted or dissolved in water. Atoms can also become stable by sharing their valence electrons. Now the thing that I want to tell you is they would rather have their own 8 valence electrons. They would rather form ionic bonds because when you transfer your electrons, one by gaining and one by sharing, what we're saying is each of those particles is going to have their own 8. When we share it, we're basically doing it long enough until something comes along allowing us to transfer those electrons to get our 8. Ionic compounds again are going to be formed between metals that want to lose electrons while nonmetals are going to want to gain electrons. Sometimes two nonmetals both want to gain electrons, but neither one is going to be willing to give theirs up, so they share their electrons. One of the things that we talked about in chapter number 6 is that thing called electronegativity. Both nonmetals want them, but neither one of them is going to have a great enough electronegativity to completely pull those electrons from the other. Covalent bond is just going to be any chemical bond that results from the sharing of electrons. And again, the reason why they form covalent bonds is because both of them have close to the same electronegativity. Basically what we formed is a molecule. 2 or more atoms that are covalently bonded together, and again, they can be of the same element. And again, we're going to look at some that are of the same element, and we'll look at some examples where they are not of the same element. When we go ahead and talk about diatomic elements, there are going to be 7 elements that can become stable by bonding with themselves. Those 7 are just going to be nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. The mnemonic that we can look at for the diatomic elements is going to be draw a 7 at number 7. You're missing 1. Go to element number 1. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. What we're saying is you're going to get an N2 molecule, an F2 molecule, or an H2 molecule. Again, those are going to be diatomic molecules where 2 atoms of the same element are going to become stable by sharing their electrons. For the rest of the year, these are going to be elements that by themselves form the diatomics. When we talk about iron, okay, iron is located right there, but iron by itself, if I would get a piece of iron, it is just going to be Fe. But the oxygen that we're breathing, that's O2. So again, any element by itself, most of the time is just going to be its element symbol. But any of the elements that are one of these 7, you will always have to write it as its diatomic. So when I talk about the rusting of iron, we're going to say iron reacts with oxygen. We're going to basically be writing Fe plus O2. So any of these, when we are talking about them by themselves, will have to be written as the diatomic. And that is going to be important for the rest of this year, especially when we get into the stoichiometry. Now, in forming these covalent bonds, they're going to do so in 3 different ways. The first one is going to be a single covalent bond. It is the sharing of 1 pair of electrons, or there are a total of 2 electrons that are being shared between the atoms. The second one's going to be a double covalent bond. We're sharing 2 pair of electrons, or we're sharing a grand total of 4 electrons. And then the last one is going to be a triple covalent bond. Again, it's going to be the sharing of 3 pair of electrons, or a grand total of 6 electrons. When you go ahead and look at each of these bonds, single, double, and triple, the more pairs of electrons that are shared, the shorter that bond length is going to become. Again, the more pairs of electrons that are shared, the shorter the bond length becomes. So looking up there, triple covalent bonds, those are going to be the shortest covalent bonds. So what do you think bond length does to bond strength? Think of a stick. The longer the stick, when I go ahead and press in the middle, I can break it very easily. But if you get a little short stick, okay, and you're holding on the ends and you're pressing in the middle, again, the shorter that stick, the stronger it's going to be, or the more force it's going to take to break it. So the shorter the bond length, the stronger the molecule is going to be held together. Triple bonds are going to end up being the strongest of the covalent bonds. Some properties of covalent bonds: they're going to have low melting points. Potentially they're going to have low boiling points. And again, they will never ever conduct electricity. We talked a little bit about electron dot diagrams, and again, they're going to be these diagrams that are going to be associated with valence electrons. Same thing can be said about Lewis dot structures. Lewis dot structures, again, are just going to be some dot structures, but now it's going to be relating the molecules, and it's going to show specifically where those electrons are being shared. So again, scientists want to know how these molecules are put together and where the sharing is going to be. So a Lewis structure is just going to be the use of an electron dot diagram to show how the electrons are arranged in molecules, specifically showing where the electrons are being shared, specifically showing where the covalent bond is. One of the things that you need to remember for this is most elements are going to have 8 dots going around it. All of the elements are going to have 8 dots going around it, while hydrogen will only need 2 to become stable. Again, the reason why hydrogen only needs 2 is because 2 will make it look like helium. And again, helium is only going to have 2 valence electrons. So what we're going to do is we're going to look at 1, 2, 3, 4, 5, 6 different examples. Okay, nitrogen, oxygen, iodine, water, carbon dioxide, and CH2O. The one thing that I'm going to tell you is when you do these assignments, I have to see the original electrons. First thing I'm going to do is I'm going to do iodine. When we go ahead and look at iodine, iodine has 7 valence electrons. Now I'm going to draw them up here a little bit different than what you were used to seeing. But again, there's our 7 valence electrons. Another iodine is going to come along, and again, it's going to have its 7 valence electrons. Now, if you notice on this one, I use the same color, but my question to you is, can you see the original 7? Well, when you look around this iodine here, you can still see the 7 dots or the 7 circles. Those represent those 7 valence electrons. When you look at this eye over here, again, when you go around it, you can see the original 7 X's. But what I'm going to do is I'm going to go ahead and draw a box around that eye. When you count all of the dots around it, you're going to notice that there are 8 of them going around. When I draw a box around the other eye, again, you go ahead and notice there are 7 original X's, and then again that 1 dot in the middle. But again, each eye is going to appear to have the 8 valence electrons going around it. And again, right in here, that's going to be my single covalent bond. That's the portion of sharing that I was talking about. So we have a single covalent bond existing for I, or for I2, that being one of your diatomics. When we look at oxygen, oxygen originally is going to have 6 valence electrons. Now when you look at oxygen, you're going to notice that there are 2 open spots. There's an open spot there where an electron can go, and there's an open spot there where an electron can go. What can happen is, to become stable, these electrons can kind of slide up and go together. So what's going to happen is, an oxygen will move the electrons together. So there are the original 6. I'm going to switch colors this time and keep with dots. Another oxygen does exactly the same thing with its valence electrons, the 2 single ones paired up. And when I go ahead and draw a box around that oxygen, you can see the 4 electrons in the middle, and you can see the other 2 pairs that are with it originally. You go around the blue oxygen, and again, you can see the 4 dots by themselves. You can see the 4 dots in the middle. Again, oxygen has, or each oxygen has, 8 valence electrons going around. Again, at that point right there, 4 valence electrons. This one's going to be a double covalent bond. And then the last one, let's look at nitrogen. Nitrogen originally looked like this, with its 5 valence electrons. Well, nitrogen will be a lot like oxygen. Those single ones are going to come together. So I'm going to switch this up. I'm going to put the 2 dots on the left side. Those single dots that came together, let's go ahead and place them there. Let's go with another nitrogen with its 3 that came together. And again, those 2 on the outside. Again, when you go ahead and look at this, look at the box going around that nitrogen. You've got 6 in the middle, 2 on the outside. 6 and 2 gives you 8. Do the same thing with the other nitrogen. Again, you have the 6 in the middle, 2 on the outside gives you 8. Again, what's going to happen here is you're going to have a triple covalent bond. The thing when you work with these Lewis structures is you're going to have to move the electrons around to become stable. You won't form any circles, okay? You won't get where they are connected back to the original. You're basically going to be forming line structures or branch structures, but they will never come back together. They will never come back around to the original atom. But move those electrons around until you get 8 of them. So what do we have left? We have water, carbon dioxide, and CH2O. If we look at water, you're going to have oxygen with its 6 original electrons, or its 6 valence electrons. Let's go to hydrogen. It has 1 valence electron always. And when I go ahead and draw my box around each hydrogen, notice there's only 2 valence electrons. But as I said earlier, hydrogen only has to have 2 valence electrons, because with 2 valence electrons, hydrogen is going to appear like helium. So hydrogen is stable now. If we draw a box around oxygen, you go ahead and look there again, you'll notice that there are 8 dots going around oxygen. So again, you have 2 single covalent bonds existing between the oxygen and hydrogen, and the oxygen and the other hydrogen. And again, oxygen itself appears to have 8 valence electrons. Now, when we look at carbon, carbon is unique. Carbon is one of those things that I'm going to draw carbon initially up here. This is what carbon initially looked like. Again, with its 4 valence electrons, 2 in the S, P negative 1, P0, and that's it. But carbon forms so many covalent bonds, and the reason why it does so is it moves its electrons around. When you look initially at carbon, you're only going to see 2 open spots. There's an open spot right there, and there's an open spot right there. There's nothing down here, so there are no electrons to share with. So carbon really only appears to have 2 open spots to bond. But to make itself so it can bond in more than one way, carbon will automatically do this. Carbon will break its paired electrons up. So now all of a sudden we have 1 dot on each side. So now we have 4 open spots for bonding. Okay. So all of a sudden an oxygen, we're going to say, moves in. We'll go ahead and draw it there with its 6 valence electrons. We'll draw another oxygen in with its 6 valence electrons. Now, when you go around oxygen, you're going to count 2, 4, 6. There's only 7 of them there. So this cannot exist because neither one is going to be stable. When you go around carbon, you're only going to see 6 of them. So we know that this cannot be correct. But in order to make this correct, you're going to find oxygen is going to rotate up. Carbon is going to rotate 1 down. So carbon now has 2 on a side. Oxygen, moving that 1 over, is now going to have 2 on a side. And let's do the same thing on the other side. Let's go ahead and look at the other oxygen. The thing is, it's going to do the same thing. That single one is going to come up. So there are the paired single ones. Here are the other 2 that were still paired up. Carbon is going to rotate 1 up. So there it is. And now, when I go around carbon, I've got 4 electrons there, 4 electrons there. So carbon has 8. Let's look at each oxygen. I've got 4 in the middle, 5, 6, 7, and 8. Let's go to the other one. 4 in the middle, 5, 6, 7, and 8. So what you're going to find out is you're going to have 2 double bonds existing. A double bond between the carbon and an oxygen, and another double bond between the carbon and the other oxygen. I know I'm drawing all of these boxes, and the reason why I'm drawing the boxes is so you can see the 8. I don't have to on your assignments see them. Okay? If you want to do something like this, I can see the 8. Again, X, X, O, X, 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 X. I can see the original electrons, and I can see that each one has 8. You do not have to draw the boxes for me unless it is going to be more beneficial for you. And then let's look at the other one, CH2O. If I look at CH2O, remember what I said about carbon. It's going to have 4 spots for bonding. All of a sudden a hydrogen is going to come in, and again remember hydrogen only has 1 electron, so it has 1 electron to donate. Another hydrogen comes in and has its 1 electron for donating. So hydrogen is already stable. Hydrogen has its 2. But now I have 1 oxygen. But the thing is, I've got an open spot there. I've got an open spot there. I'm hoping you'll remember kind of what we did with the last ones. Anytime you have open spots and only 1 element to deal with, thing is, these are going to pair up. Okay? It's going to slide down. And when it slides down, it's going to be paired up. All of a sudden, oxygen comes, takes its electrons and its 2 open spots and pairs up, because remember, oxygen initially looked like that. So again, if carbon paired its single ones up, oxygen will pair its single ones up to do this here. And again, when you look at hydrogen, there's 2. When you look at this hydrogen, there's its 2. Let's look at carbon. 2 there, 2 there, that gives me 4, and the 4 in the middle give me 8. If we go to oxygen, we have the 4 in the middle, 5, 6, 7, and 8. Just remember what I said. All of the elements will have to have 8 electrons going around it. Hydrogen will only have to have 2. When we go ahead and talk about energy, and we're getting ahead a little bit, I know we're talking about chemical bonding and ionic bonds and covalent bonds and things like that. But in every chemical reaction, bonds in reactant molecules are going to be broken. New bonds are going to be formed. Sometimes you just have them broken, sometimes you just have them made, sometimes you have them broken and made all together. There's 2 types of reactions that we need to look at, or 2 types of energy changes. The first one is going to be an endothermic reaction. In this one, energy is going to be absorbed in the reaction. And if energy is absorbed in the reaction, the environment, the surroundings are going to become colder. Exothermic reaction is going to release energy. This is like a wood-burning stove. You burn the wood, and guess what? It heats the living room. It heats the basement. So we are getting the energy. And if it's giving out energy, or if it is putting out energy, the thing is, the environment is going to become warmer. Endothermic reactions, environment becomes colder. Exothermic reaction, environment becomes cooler. And here's a couple different graphs. The thing that I want to tell you, SM is just going to be our starting materials. P is going to stand for the products, or what's produced. So when you look at an endothermic reaction, we said energy is put in to the reaction. So this is the energy that I'm talking about. Energy's put in, and notice what happens. The final resulting product, it has more energy than what we started with. The product has more energy than what we started with because we added energy to the starting materials. On the other hand, if we look at an exothermic reaction, here's our starting material. For example, wood. You light it on fire. It releases all of this energy down here. All of that energy is released from the breaking of those bonds. And look down here. What's left after you burn a bunch of wood? The ash. And what we're saying is the product, or ash, has a lot less energy than the original wood itself, because the products have less energy than the starting materials had. Okay, so endothermic products end up higher than the starting materials. In an exothermic reaction, all of that energy is given off, so the products have less energy than what we started with.